We are on the module 4, dealing with groundwater heat pumps. In the submodule 4.2, I will tell you something about the techniques, how to characterize our site to successfully implement a groundwater heat pump system. For this, we have to know the equation, how much heat can we abstract from the underground, from our aquifer. If we have an advective heat mechanism, what we have in the groundwater. So this means that the heat is carried by a particle of the media of our fluid, so in our case of the groundwater, and is moved from one location to another. So the heat is stored by our media and then move it with the media. So for that, we have to know what is the specific fluid heat capacity and the density of our fluid, in our case groundwater, and for water it is quite well-known parameters. And these parameters, the capacity and density, varies a little bit with temperature, but the temperature variation in groundwater is not so high that also these parameters are more or less constant. What we have to know is also the temperature difference. So we have to know the initial groundwater temperature and then the temperature of what we want to use later on. So we have to assess the initial groundwater temperature. This I will explain a little bit more in the part 3 of this lecture. So of most importance is the volume. So how much volume can be extracted from our aquifer, so from our groundwater. And this is defined more or less by the 3 parameters: hydraulic conductivity, groundwater thickness, and hydraulic gradient. Hydraulic conductivity is based on the porosity of rocks, so with high porosity or low porosity, or the so-called effective porosity, so how much water can flow through my underground and through my underground media. The groundwater thickness is just the saturated part of our aquifer. So how much water is available on a specific location, or the water column at a specific location, what can be used. And the third parameter is a hydraulic gradient. Hydraulic gradient is the difference between the groundwater head at 2 specific locations. So water flows from a high hydraulic head to a low hydraulic head, or from high hydraulic potential to low hydraulic potential. So the hydraulic gradient defines also the flow direction. This is why we need it. So starting with the groundwater thickness, these are the parameters we have to assess first. And how do we assess the groundwater thickness, or the saturated groundwater thickness? You see here 2 red arrows. The top arrow actually defines the water table. So we have to measure the water table at our location. And the bottom red arrow actually defines what is the basis of our aquifer. So what is the boundary between our aquifer and the aquiclude? So between a matrix or a geological horizon that has a high hydraulic conductivity and what is below with a low hydraulic conductivity. This is what we have to define. Normally, we do it by doing some cross sections. So the black lines here are boreholes, and what you see here in yellow, this is the aquiclude. So this is geological horizons, rocks with a low hydraulic conductivity, and the white one is our aquifer, and the blue parts of this aquifer is the saturated thickness. And what you here see is that we have, or that we can have, also a quite high relief. So we have zones where we have channels, and then we have plateaus, and this defines also if we have more groundwater available or less groundwater available. So how we do that normally, of course, we interpret boreholes and the lithological description of boreholes. Here on the left side, you see some boreholes and descriptions. The yellow ones are gravels, and the orange ones are sands. And Brown and violet colors is clay and silt. So we define here now by the interpretation of boreholes then the basement of our aquifer. And we draw cross sections or we do some 3D models as you see in the next picture here. So we have here a complex 3D model. The red lines are the drillings and the boreholes, and the white parts here are filter sections, what we defined here, and the blue bodies are the groundwater bodies, what we assessed here in a 3D model. So it can be quite complex, but it can be also described by cross sections and borehole interpretations at a specific location, of course. So here's an example of such a relief of an aquifer. You see some channels and some plateaus as we described before. And of course, then what you have to do is to measure the groundwater table. You see some measure devices here at the top and some observation wells. It can be observation wells under surface or above surface. And then you have to measure the distance between the surface and the groundwater table. And then with that, with a lot of such measurements, actually, you can interpolate a groundwater table map or a groundwater head map or a groundwater potential map. So you can define flow lines. You see from high hydraulic potential to low hydraulic potential, the water flows in that direction. And you can define what is the saturated thickness at a specific point. In our next picture, you see that as an example, again from Munich. So we overlay here the relief, you see on the right side, with the measurements of the groundwater, and then you get the groundwater thickness. In the light blue colors, it is a low groundwater thickness, so you have not a lot groundwater available, and the dark blue colors are actually explain that there are more groundwater available. So this is essential to see how much groundwater can be used, and we will explain the hydraulic conductivity now in the next part.